Good evening from Dhaka, Bangladesh. I'm Altaf Hussain, former professor, Department of Chemistry, University of Dhaka. I was organizing a AS and A-level chemistry lecture series, and this is the 38th lecture, and this is on transition metals. Well, 37th lecture was also on transition metals. We started some properties, physical and chemical properties of transition metals, specifically the transition metals in the period 4, which is in the syllabus of A-level chemistry. Therefore, we are concentrated our discussion in transition metals in period 4, that is scandium to zinc, only this. Rest is a vast number of transition metals, and it has almost a separate branch of chemistry, which we call coordination chemistry. Okay, some physical properties and chemical properties we discussed, and also the possible structures of transition elements. Now we will talk about copper, and it is the least reactive for transition metals in period 4. It does not react with mineral acids, that means hydrochloric acid or sulfuric acid. It oxidizes only very slowly with in moisture. Therefore, copper is a very good conductor of electricity, and you can make many type of brass and bronze with copper. An example here, saxophones is made of brass. Here is saxophone made of brass. What is brass then? This brass is the alloy of 60 to 80% copper and 20 to 40% zinc. We can prepare many different kind of alloys with transition metals. Well, we have been discussing about hydrogen ion, aqueous hydrogen ion, you see. And this shows a very simple formula, but it does not represent a simple formula like this. In acidic solution, we do get a hydronium, oxonium, or oxonium ion. What happens that this is in water molecule, we have discussed it, and then we have lone pairs of electron, 2 lone pairs of electrons. One of the lone pair of electrons form a bond with the hydrogen ion, and that is called hydronium ion. And like we call it a coordination bond or dative covalent bond in this one. Like this hydrogen ion, transition metals like copper 2, silver ion, etc., also form chromium 3, also form aqueous complex ion. And here is the formula of chromium aqua complex ion, copper aqua complex ion, silver aqua complex ion. And as because this chromium, copper, and silver, the charge of these are size and of these cations are much bigger in size than that of hydrogen ion. Therefore, it can accommodate 6 water molecules, you see, 6 water molecules. Here is a shape of a copper 2 aqua ion, and here is the shape of chromium amine ion. This is an octahedral shape. We can also have platinum, chloroplatinum ion, a complex ion, which is having a 4 chloride ion in a planar way, and then this is a planar molecule. This is a tetrahedral molecule. This one is a linear molecule. We will come to this a little bit later in this next slide also. Let's talk about this slide. Well, you see, we know very well that d orbitals are 5 orbitals, and the shape of these d orbitals are like this. Then we have this d yz orbitals, this is d xz orbital, this is d xy orbital, and this orbital we call dx square minus y square, and this is the z square orbitals. why I'm talking about this, how we can get colored ion specifically when we have these 5 orbitals. These 5 orbitals, when we call it degenerate orbitals. When I call it degenerate orbitals, that it means that all the 5 are having same energy level. This is the same energy level. But when this ligand approaches to this copper-2 ion, then it splits into 2 sets of orbitals. The one set is like this, dx squared minus y squared and dz squared. And another set is this dxy, yz, dxz, and xy. And you can see that these 2 are not in same energy level. We said that we call degenerate orbitals when orbitals are in same energy level. But here it is a slight difference in energy, and therefore it is no longer, it is degenerate, but when split it into 2, it's no longer degenerated. We call it non-degenerate orbitals. So that's energy level absorbed if it from the visible spectrum, and then we see that this pair of electron here repels each other, and that it jumps to the higher energy level, and thereby the complex form here becomes colored, and that is what we can explain the color of the color and shape of the complex ion. Now we go to the next slide. And then how do we name the complex ion? There are simple 4 rules that identify the number of ligands and then name the ligand. And then which is the central metal ion, look to it. And this metal ion is a Latinized name ending in 8, if for negative complex ion, but for positive ion, it's simple English name, iron, copper, etc. And finally, we have to say the oxidation number of the central metal ion. Okay, we take example here. This is the complex ion, 4 complex ion here. So here we have 2 ligand, ammonia. We call this name as amine. But do remember that organic amine, this ammonia complex, have been named, written, spelling is different here. So we call it diamino, then silver, because it is a positive ion, diamino silver. And what is the oxidation state? Because ammonia is neutral, and therefore here oxidation state of silver is +1. So therefore we call this diamino silver 1 complex ion. Okay, we go to this. Then you see we have 6 ligand, water ligand, and copper, and it is a cation. So hexa, water, we use Latin name aqua, hexa, aqua, copper, and its oxidation state is 2. So therefore it's hexa, aqua, copper 2. But if you take this one, then what you see that it is copper and ligand is chloride ion, and there are 4 chloride ions, so we call it tetra, chloride for chloro, tetrachloro. And what is it? It's an anion, and therefore it's cuprate. Cuprate, and oxidation state of copper is 2. So we call it tetrachlorocuprate 2 ion. Similarly, hexa, this is cyanide, hexacyanoferrate, and because cyanide ion is 1 negative ion, therefore it is 3 positive charge here. So hexacyanoferrate 3 ion. So this is how we name the complex ion. Now we go to the next one. Well, then if we have ligand, only 1 ligand, that means from the ligand, only 1 lone pair is donated to the cation, and therefore form a covalent bond with only one lone pair of the ligand. So this is, we call this monodentate ligand. And monodentate, it is one tooth to hold onto the central cation. And the monodentate ligands are water, ammonia is neutral, there is no charge, chloride ion, hydroxyl ion, cyanide ion, these are all monodentate ion. That means dative bond formation is done by this oxygen lone pair. Here the nitrogen lone pair, and chloride has got lots of lone pair, hydroxyl ion also, and then cyanide also. So this is what is, if one ligand, we call it monodentate ligand. And then some ligands have more than one lone pair. And then if it is two lone pair, we call it bidentate. And some ligand has more than even two lone pairs. So we call that multidentate ligand. For example, EDTA, ethylene diamine tetraacetylacid, EDTA has got 6 coordinate covalent bond forms, and therefore it's multidentate ligands. So we can have monodentate ligand, we can have bidentate ligand, we can have multidentate ligand, and here are the complexes of this nickel complex, bidentate ligand. Here's the nickel, here's bidentate, this ethylene ion. This has got, you see, this nitrogen, and this nitrogen is forming complex ion. This nitrogen is forming complex ion, this one and this one also. Similarly, EDTA form complex ion, which is a multidentate ligand. We can have also ligand exchange reactions. And there are 3 types of ligand exchange reactions. The first one, by exchanging one ligand for another. These exchange reactions are often reversible reactions. Do remember that these are reversible reactions. And sometimes this exchange ligand accompanied by color change too. We take an example of concentrated ammonia solution is added to a copper sulfate solution. Ammonia molecules are exchanged for water molecules around the central copper ion, and the color changes deep blue. We are taking here that here is the copper hexa aqua copper 2 ion solution, which is pale blue solution. And then we adding alkali to it, what we get is tetra aqua copper hydroxy dihydroxy compound, and that is a pale blue precipitate. When this pale blue precipitate, we use excess ammonia, we get a deep blue solution, changing this water molecule, changing to ammonia molecule. So this ligand, ammonia and water, are both uncharged and similar in size. So one can easily exchange this ligand and form a change in coordination number, and it does not change any coordination number either. So no change in coordination number, and only a change we get at the ligand change, and also accompanied by color change. This is one type of ligand exchange reaction. Another type of ligand exchange reaction has occurred. Another type of ligand exchange. Example, you can take a concentrated hydrochloric acid added to copper sulfate solution. We have copper sulfate solution. This is a plain blue solution. Here it is. And then we add the concentrated hydrochloric acid, we get yellow solution. So, so the water molecule has been replaced by chloride ion. And the ligand exchange change in coordination number. Here it is 6 coordination number. Here it is 4 coordination number. So change in coordination number as well as color change happens. If we go to the next slide, we can another example of color changes. This is a octahedral pink solution of cobalt. And if we add hydrochloric acid to concentrated hydrochloric acid, we get a tetrahedral shape. You see that the shape of the iron is also changing, tetrahedral shape. So here, coordination number change, shape change, color change happens. There are lots of ligand exchange reactions in living organism. For example, hemoglobin is the red protein blood which carries oxygen from the lungs to the cells in the body's tissues. Well, it has got four polypeptide chains. This is four polypeptide chain, and this is the iron complex and hemoglobin. We call it hemoglobin. Okay, heme growth. So it is a multidentate ligand, and then a pair of electron is there in oxygen molecules. So this is oxyhemoglobin, which is bright red, or a water molecule, it becomes deoxyhemoglobin, which is dull red. There's reaction between heme groups and hemoglobin pick up the release in oxygen, etc. But do remember, carbon monoxide cannot be reversible reaction. It's an irreversible reaction, and therefore we call carbon monoxide is a dangerously toxic gas for the human body. Polypeptide ligand, such as EDTA, replaces monodentate ligand to larger increase occurs in the entropy of the system. We go to the next slide, and there, as we see, this is a reversible reaction. So here is a reversible reaction. We are changing tetra hexa aqua copper 2 ion to bichloride ion, and we get cuprate, tetrachlorocuprate 2 ion. So since it's a reversible reaction, it can have equilibrium also. So the equilibrium constant, we write it like this. Is it not? We have shown how we do in reversible reaction the equilibrium constant. We can calculate it. We can experimentally determine it, etc. In the case of complex ion, we replace this Kc by K-stab, that is stability constant of complex ion. And we can measure the stability constant of the complex ion like this. This chloride ligand and having tetrachlorocuprate 2, its stability constant 4.0 into 10 to the power 5. Ammonia, its stability constant 1.3 into 10 to the power 13. And EDTA, copper EDTA complex, which is stability constant 6.3 10 to the power 8. So what this means, the higher the stability constant, the more stable is the complex ion. Now we take some of the reactions of transition metals with aqueous alkali. Okay, you can see that this is chromium 3 ion. When we add sodium hydroxide in this solution, we get a green precipitate, which in excess reagent, that means we add excess hydrochloric acid, this precipitate dissolves and we get dark green solution. If we do the same reaction with ammonia, we will see the gray-green precipitate slightly soluble in excess reagent to give a purple solution. So we are having a ligand exchange reactions. For iron, 2 dirty green precipitate soluble in excess reagent, green precipitate insoluble in excess reagent. So we are talking about hydroxyl ion and also has ammonia ion. So therefore, we have different type of reaction with chromium, with iron 3, with cobalt 2, and copper 2 ion. So that is what is some reaction with aqueous alkali. And these very few reactions we do discuss in the A-level chemistry, but whenever we go to the university or higher chemistry, we will see that there are many different kinds of reaction with aqueous transition metal ions. Okay, next we are talking about the catalyst-based transition elements and their compounds. There are different types of catalyst formed by transition elements, or even its compounds. So a few examples are there. Vanadium 5 oxides, we use it in the contact process of manufacture of sulfuric acid. iron trioxide for Haver's process of manufacture of ammonia, nickel, palladium, or platinum. This we hydrogenation of unsaturated vegetable oils. We use it. Platinum or platinum rhodium alloys that can be also a very good example of catalyst. So conversion of nitrogen oxide and carbon monoxide can be done by platinum or platinum rhodium alloys in catalytic conversion vehicles to get carbon dioxide and nitrogen. Platinum we can use, though it's very costly, but platinum we can use reforming the straight chain alkenes to cyclic alkenes. This is straight chain alkenes heptanes, and you get a methyl benzene by this catalytic reaction. So if we now classify the catalyst, we will see that there are two types of catalyst. Of course, we will have more types of catalyst when we study catalyst in advanced level. But in general, we can have two major different types of catalyst, and one is called heterogeneous catalyst, and another is homogeneous catalyst. Heterogeneous catalyst, which one is heterogeneous catalyst? The catalyst involved in this reaction is in different state than that of reactants. We call it heterogeneous catalyst. Okay. Catalyst involved in the same state of the reactants, we call it homogeneous catalyst. So every catalyst has got a different important applications of the catalyst. And there are a few reactions I mentioned here. For example, the peroxidized sulfate 6 ions can be used as a catalyst to oxidized iodide ion to iodine. And this reaction happens on very slow, but if you use iron 3 ions, it becomes very faster reaction, many times faster reaction. So we do have catalyst also, which reactant becomes product in the reaction, products becomes a catalyst, and that what we call autocatalyst. An example is the manganese ions is acting as the autocatalyst for this reaction. So the ethanodiide ions and manganese 7 reactions from where we get manganese 2, but this is becoming an autocatalyst forming this ion. So this catalyst is it's a challenging one in priority areas of chemical research. People are trying to develop new and improved catalyst, and specifically drive greener world and a greener future with catalyst. So the properties of catalyst here we mentioned: speed up reactions at operate at low temperature, high atomic economy, less waste, high selectivity, etc., without the waste from side reactions, etc. These are the very challenging things people are doing and doing the advanced research level. With this, we will finish our lecture today, and next lecture will be redox reaction of type 2. Specifically, we talk about electrochemistry in the next lecture. Thank you very much for listening this one. Thank you so much.